Hello friends, welcome back to our channel STM Mechatronics. So in this video we will see how to code the STM controller in bare metal programming. So we are going to start the bare metal programming tutorial, and that will be a new series. So before starting this bare metal programming series on STM32F401 CCU6, I want you to download two things. First one is the datasheet of STM32F401, okay, and second one is the user manual. So this is the user manual of STM32F401 CCU6. Okay, you can see over here. So it consists of STM32F4040 series. Okay, we are going to use 401 CCU6. So this reference manual will be applicable for that also. Okay, now what we need to do is, like, first we will see like the peripherals that are available in 401 CCU6. Then we will see how we can implement the code, how to write the code, and how to create a new project. So all these things we will see. Okay, so if you go through this like data sheet, you will be able to see that there are different peripherals available, different number of IO ports available. Okay, so here if you see in STM32F401 CCU6, you can see that the memory available, flash memory available, will be up to 256 KB of flash memory. Okay, that is sufficient to write our program. Then up to 64 kilobytes of SRAM, that is RAM. Generally, to like above 4 kilobytes, we can install the FreeRTOS on our controller. Okay, we will see that how to implement the FreeRTOS on STM32F401 in next series. Okay, but apart from these, like, these are the memories. Apart from these memories, you can see up to 81 IO ports with interrupt capabilities, like 3 I2C, 3 UART, 4 SPI. So total 6 plus 4, 10, and 1 SDIO interface. It is available on 401 CCU6. Right? Apart from that, CRC calculation unit is there, RTC is there, right? Then general purpose DMA is there, up to 11 timers are there, 112-bit ADC is there. Okay, so these are all the peripherals that are available on our controller. Now, before starting this explanation, or what we are going to see, or what we are going to do, right, I will be showing you a demo. Here in the block diagram, you can see like which peripherals are connected to which bus and which peripherals are available. So if you take like timer 1 is connected to APB2 peripheral, which in turn is connected to AHB peripheral. Okay, now the GPIOs are connected directly to the AHB1 peripheral. Okay, so here you can see that GPIO are connected directly to the AHB1 peripheral. Okay, now there are different peripherals available like USB, then timers, different timers, USART, SPI, I2C, okay, RTC. So going forward, like, we will see the memory. We are interested in how the peripherals are assigned. Now we have seen that different peripherals are connected on different bus, right? So we will see where these peripherals are located in the in the buses, right? So in AHB2, you can see the USB OTG. DMA1 and 2 are connected to AHB1. Then RCC is connected to AHB1. CRC is also connected to AHB1, which goes up to 84 MHz that we have seen in the block diagram. Now the GPIOs are connected to AHB1 bus. Okay, coming to APB2 bus, the SPI, SDIO, SPI4, right? External interrupts, timer 9, 10, 11. These are connected to APB2. Okay, ADC1 is connected to APB2. USART is connected to APB2. USART6 is connected to APB2. Now, here you can see, along with the like peripherals which are connected to different buses, you can see the addresses also. Okay, so if we see for AHB1, the base address is like 4002.0x00. This is the base address. And for GPIO A registers, like there are different resistors for different peripherals, right? The n number of resistors are located between this boundary. So from 4002 0000 to 04002 03FF, right? So between these memory, the different registers are located of GPIO A. Okay, we will be using these registers in order to configure our GPIO A. Okay, so these are the base addresses that we have seen. Okay, now these are the different peripheral buses that we have seen, the peripherals which are connected to buses that we have seen. Okay, this is the important information that we have extracted from the datasheet. Now, like going back to the user manual. Okay, first, the agenda for this video will be like to toggle the GPIO pin. It will be very simple. First tutorial will be very simple. Just toggle the GPIO pin, right? So that we will be able to get this waveform, right? Square waveform. Now, if you see, right, we have connected it to GPIO A P1. Okay, we have connected one red LED on STM32F401 CCU6. Apart from this, we have not done anything. Okay, we have simply loaded our program. If you go, okay, this is the program that we have loaded. And our LED is toggling. So basically our GPIO port is toggling, pin is toggling, and that's why the LED is getting on, off, on, off, on, off. Okay. Now, why bare metal? So if you see in main.c, you won't be seeing any configuration, right? Which is generated by STM32 CubeMX, right? So there is no CubeMX configuration, which gives us a whole bunch of configuration for RCC, for GPIOs, right? So our code is very simple. The main.c is very simple. We have created one delay over here, that is a user defined delay. Okay, then the simple function, in this function, like we have configured our GPIO as an output port. Okay, and we have given a GPIO handle. Now we have included some files, gpio.h and STM32F401xx.h, right? These two files we have included. Now first we will go into STM32F401xx.h. Okay, in this file we have included standard input output. Okay, standard int.h. If we have not included this file, right, so this uint32 will give an error. So for that we have to include this stdint.h. Okay, now we have defined one micro underscore vo for volatile. So wherever we are going to use this macro, it will be replaced by volatile keyword. So all these things, right, in the GPIO rich def structure, these are all volatile variables. Okay, why volatiles? Because these are pointing to certain memory locations, right? And if any change done by the external hardware, right, or any change made by the hardware will reflect into this register values, and we want to read those updated values at the runtime. Okay, so that's why we have made it volatile. Now we have defined some other macros like enable, disable, set, reset, GPIO pin set, GPIO pin reset, flags reset, flag set. Okay, and we have given, like for enable and disable we have given values as, for enable we have given value as 1, for disable we have given value as 0. Okay, and then we have reused enable and disable to assign those values to other macros. Okay, now you will be seeing like there are different addresses, memory addresses that we have given. Now we have created these macros for the addresses, right? while writing the bare metal programming, we won't be going into the data sheet and continuously watching, okay, we want to write at this memory location, so we will be writing at the memory location. It will become very tedious job. Okay, instead what we will do is we will create certain macros and names for that addresses. Okay, and then we will use those macros instead of the memory addresses directly. So as I mentioned, like in the datasheet, right? If you see AHB2, the base address for AHB2 is this 0x50000000, right? For AHB2, the base address is 50000000. Okay, so we have created macro for that. Similarly for AHB1, APB1, APB2. Okay, now again, coming back over here, we can see that GPIO A is connected to AHB1 and its address is 40020000. So the base address plus 0 will be the address for the GPIO A. So you can see that GPIO A is connected to AHB1 plus offset of 0. Okay, so we have connected. Now you will say, okay, that's fine for the GPIO A, but what for GPIO B, right? So for GPIO B, you can see that like this is the 0000 is the base address plus 0x400 will be the offset for GPIO B. Okay, so here you can see that AHB1 address, base address plus 0x4000 will be the GPIO B base address, right? Similarly, we have created for up to GPIO I. Okay, base addresses up to GPIO I. Now, again, coming back to RCC register. So, RCC register is located at 3800, 4002 3800. So, 4002 is the base address for AHB1 bus, right? And for RCC, what will be the offset? So, 0x3800 will be the offset. Okay, so we are creating a macro base address plus 3800. This will be the RCC base address. Okay, now like in this file you can see that for GPIO regdef I have added too many values or too many variables in the structure, right? For RCC, again, I have added too many structure variables, right? So why we have created like this, that I'll explain it to you. So coming back in the user manual, right? If you go to the RCC registers, right? We know that the base address, right, for RCC, it is 4002 3800. Okay, so address offset is 74H, right? Now if you see, like coming back over here, RCC clock register and status control, right? So in RCC, if you scroll it down, here you can see the register map for different controllers, right? We want to see the check the register map for RCC register map for STM32F401 series, right? So we'll scroll it down. So this will be the same for this register map will be same for STM32F401 XX also. Okay, so the address offset will be 0x00 at 00 offset. it will be RCC CR register. Okay, so RCC CR is 32-bit register and it has different configuration bits in it. Okay, so each register is of 32 bits. So that's why what we have done is we have given it as a volatile uint32. Okay, and CR, first register is of CR, its offset is 00. Okay, then coming back, RCC PLL CFGR. Okay, now PLL CFGR, its offset is 0x04. Okay, its offset is 0x04. Then RCC CFGR, its offset is 0x08. RCC CFGR, its offset is 0x08. Okay, likewise we have created the structure variables such that these all the things will map it to it. Now in between you can see that we have kept some result values, right? Result 0. So result 0 variable, it is on the like offset of 1c, right? Now if you go here, we can see that a 32-bit value is resolved. Alright, so we are not going to use that. We are not allowed to use that basically. So that for that, like we have not marked it as volatile. We have simply kept this variable as result uint32. uint32 result 0 on the offset of 0x1c. Okay. So this way we have created the RCC register regdef structure. Okay. Similar way we have created GPIO regdef T. Okay. Now why we have created this RCC regdef structure is RCC stands for reset and clock control. Okay. So each peripheral is connected to different buses. So now while using that peripheral, what we have to do is we have to enable the clock for that peripheral, right? So in this video what we are going to do is we are going to configure GPIO A pin 1 as output, right? So first step will be like to enable the clock for GPIO A, correct? But GPIO A is in AHB1 and RCC register is also in AHB1. That's why we have written all those different registers in RCC, right? So what we have to do is like we have written it different. So if you see this is control register, then PLL clock configuration, then clock configuration, right? Now AHB1 reset, AHB2 reset, AHB3 reset, right? APB1 reset, APB2 reset, right? AHB1 ENR, AHB2 ENR, AHB3 ENR, right? Then APB1 ENR, APB2 ENR. Now we know that like our GPIO A is connected to AHB1, right? That's why we'll have to go over here and write the value in the respective bit so that the clock for GPIO A will be enabled, right? Now if you go inside here, we will see this will be the control register, right? Now we can see that there are different reset values. Clock control register 83, right? 0x000083, right? 83 will stand for 10000011. So by default HSI internal clock will be on, right? So if you see 111 will be written. So HSI on, right? HSE oscillator is on. Sorry, not this, bit 0, HSI on, right? Internal high speed clock will be enabled. So we are going to use the internal high speed clock, that is RC clock. Okay. So this is by default, that's why we are not going to touch that register. Okay. Now we will be using this AHB1 peripheral reset. Now not reset, we want to use the enable, right? Yeah. So we are going to use this AHB1 ENR. Now if you see, we want to enable the GPIO A, enable clock for GPIO A, right? It is on GPIO A, enable, it is on bit 0. So if you go here, right, bit 0, if you read the description, it says like GPIO A enable, IO port A clock enable, right? We want to enable the clock for GPIO A. So what we'll have to do is we'll have to write 1 to it. Okay. So what we'll have to do is we'll have to write 1 to this port. Sorry, 1 to this bit, right? 1 to this bit. RCC AHB1 ENR equals to 0x00000001. That will be the value, right, to enable the port A. Now if we go over here, right, AHB1 ENR, we will have to write the value 0x00000001 over here. Okay, and we'll go over here, we'll check. Correct. So to enable the clock for GPIO A, we'll have to write RCC AHB1 ENR and GPIO A enable, right? If you see, GPIO A enable is on bit number 0. Okay, so we are going to write 1 to bit number 0, right? So we are going to write 1 to bit number 0 of RCC AHB1 ENR so that our GPIO A peripheral clock will be enabled. Okay, so this way we have done it, right? Now this is the value. Okay, I'm going to upload this project on my GitHub, and I will be sharing the GitHub link in my video, so you can download that, you can try that, right? Now first, like, we have understood this RCC structure, RCC's regdef structure. Okay, now we know that, like, we are going to use certain values, right? We know that the RCC base address is this. Okay, and this is the structure. So what we are going to do is we are going to use a structure pointer, RCC regdef pointer, to this base address. Okay, so what will implement is, like, from this address, right? So this will be the base address for CR, right? And for the different registers, right, it will go on pointing. So we can access all these registers using this pointer, structure pointer. Okay, so for that we have given a name RCC. Okay, now if you see in GPIO.h, we have used the RCC. It is indirect access to structure members, right? Not a direct access, because RCC is a pointer. Okay, and AHB1 ENR. Then we have enabled peripheral clock of GPIO A. Okay, similarly we have enabled peripheral clocks for other things. Okay, what over here we have disabled the peripheral clocks. Simple thing. Okay, so in GPIO.h, these are the different macros that we have created for enable and disable or of peripheral clocks. Okay, now we'll come over here, we'll understand the GPIO regdef structure. Okay, now as I have mentioned that we have understood this part, right? Till now we have understood this part. Now in general purpose IO, we'll go over here and we'll see the register map. Okay, so again in the GPIO registers, right, we have different kinds of registers for configuration. So GPIO can be used as the input, output, alternate functions, right? So three way we can use the GPIOs. So what we can do is, like, we will need the register map. On 0x00 we have mode registers, mode R, right? On 0x04 we have output type register. On 0x08 we have speed register, output speed register. On 0x0C we have pull up pull down register. Okay. On 0x10 we have input direction register. On 0x14 we have output direction register. On 0x18 we have bit set reset register. On 0x1C we have lock register. On 20 we have alternate functionality low, and on 24 we have alternate functionality high registers. Okay, so first register is of like mode register. First register is mode register. It is on the offset of 0x00. Second register is output type register. It is on the offset of 0x04. Right. Then third register is output speed register. It is on the offset of 0x08. Right. Then pull up pull down, PUPDR. Right. After PUPDR we have input direction, output direction, and BSRR. After PUPDR we have input direction, output direction, and BSRR. After BSRR what we have? Lock register, then AFRL and AFRH. Okay, so we have lock register and alternate functionality. For alternate functionality we have two registers, each of 32 bits. So for that we have created an array of two registers, each of 32 bits. Right. So this is the register definition for GPIO. Right. Now this register definition will be, or these sub registers for GPIO A, these will be same for each register, sorry, each GPIO. Okay, let it be GPIO A or GPIO B or GPIO C or GPIO D or GPIO E or GPIO F. Okay, let it be any register, any GPIO, right? These registers will be common for all the GPIO peripherals. Okay. Now, in order to achieve the output functionality, what we will have to do is we'll have to configure few of these registers. Okay. So here in STM32F401 XX.h, what we have done is we have defined like GPIO A, we have created macros. Okay, for GPIO A, for accessing the structure, we have created these macros for accessing the structure member of GPIO regdef T. Okay, so the macro is like GPIO A, structure pointer, GPIO regdef pointer, and we have given the base address of GPIO A. Okay, so if you see, we have already created this macro, right, and assigned the base address of GPIO A to it, and here we have created the structure pointer. Now using this pointer we can access the GPIO regdef structure members indirectly. Okay, now coming to GPIO.h, we have 16 pins on each GPIO. So for each GPIO we have created like this. Okay, now as I mentioned, right, the GPIO can be used as input or output or alternate functionality or analog. Right, these are the four modes in which a GPIO pin can operate. Okay, so for each input, output, alternate functionality and analog, we have created these macros. Okay, now our GPIO, if configured as output, can be like we have the internal pull up or pull down. It can be configured as output drain, open drain or push pull type. Okay, so here we have pull up or pull down. So these macros are created for pull up and pull down. Okay, so if we want to have no pull up and pull down, the value can be set to 0. If you want pull up, the value will be set to 1. If you have pull down, the value will be set to 2, and pin reserved, for that we have value set as 3. We have different kinds of speed modes or speed settings for each GPIO pin. it is low, medium, fast and high. For this we have created these macros. Okay, so this is the contents for GPIO.h file. Okay, so here you can see this.